So this is our final lesson together, guys. Lesson 8, History of the Atom. I normally start with this, but I know you've done a lot of this with Mr. Dolan already, and there's quite a big overlap. So I'm not going to bore you with all of it, but I am going to focus on the main bits from the physicist's point of view. So it starts off with Democritus and with an idea. In mathematics, the Greeks had proven you could take number 1, you could half it, and you could have a half. And you could carry on halving it for infinity. So they discovered the concept of infinity. You can take something and keep halving it forever. And it was Democritus that said, well, what if you take mass and you half it and you half it and you half it? Can you go forever? And he decided no. He decided you would reach atomos, the not cuttable unit of matter. They had no concept of what those atoms might be, what they would look like, the size of them. But the atomic theory is a good 2,500 years old. It wasn't until the early 1800s, though, that we really started getting going on this. So through the work of Thomson, and that's where I'm going to start, we had discovered some of the particles of an atom, but the question was, how were they laid out? And so Thomson proposed what was called, let me get rid of those a minute, Thomson proposed what was called the plum pudding model. Now, we needed to test this model, and that's how science works. You come up with a model. If you can't test it, it's not science. So here we have the plum pudding model, which is a blob of positive charge interdispersed with negative electrons. And a scientist called Ernest Rutherford, a New Zealander who'd lived over in England for a long time, was a fantastic experimentalist, and he decided to test this theory out. So he took alpha particles, which, if you remember from lesson 3, are 2 protons and 2 neutrons. We have them up at the side there. And he fired those alpha particles at a sheet of gold, and the gold was hammered out to be just a few atoms thick. Now, if the plum pudding model was true, then those alpha particles would have passed straight through. But that's not what he saw. If we go over to what he actually saw, we saw that some of the electrons were actually deflected. Now, I can make them heavier, and the deflection will be greater. Oh, yeah, there we go. So what he discovered was that while most of the alpha particles did pass through, some were deflected at very steep angles. There goes one now, to the left. There we go. So I'm going to take a screen grab of both of these. And I'm going to bung them over into my model. I'm going to wait till one of them's at a really steep angle. Should happen any second now. Come on, one to the side. Ready. I'm going to grab... I want one that goes off to the side, right off backwards almost. Oh, now it doesn't happen. Come on, come on, come on, one more. I'll take that. Okay, so this is the bit I really want to focus on, this point in history here. It's the experiment by Ernest Rutherford. And it's called well, it got named after him at the beginning, but it's a gold scattering experiment. We'll just put XP. So, like I said, we can actually bring up what it looked like. Alpha gold scattering. We'll have a look at the practical that he actually used. Hopefully there should be an image of it. Here we go. I was hoping for a photo, but I'll take this. So we have a source of alpha particles, a radioactive substance. We shoot it into a vacuum tube. So you don't want any particles here because, if you remember, alpha is highly ionizing and they just get absorbed. Most of them deflected through, but some were scattered, so they'd interacted with the nucleus, but some of them had completely reflected off, which showed that most of it was empty space, but that there was a highly concentrated, dense core for the nucleus. So if we were to draw a top-down view, so of alpha shooting through. We'll go for a gold colour. Let's make it thicker. Gold there. There's my sheet of gold leaf. Then we'll draw the traces of the alphas. So we'll draw them like this. Most of them carried through. Some deflected. But, and these were the really crucial ones, some, REC sending me a really important thing, some of them deflected massively. So inside a vacuum, let's go smaller, a vacuum tube. And all around the edges we had detectors that measured the tiny electrical current by the +2 charge. So you'd have detectors around here. And the key bit is number 1. We'll label these parts number 1 and number 2. So I'll write them on the next page. Number 1, most alphas passed through. And what did that mean? That means most of an atom is a vacuum. And we'll put empty space. Empty space. But number 2 showed us that alpha particles must have deflected off a heavy, dense nucleus. Okay, I'm going to colour code those. So most goes through, and that means it's empty space, but those that were deflected must have hit a heavy, dense nucleus. And so we came up with the nuclear model. And a nuclear model just means where most of the matter is distributed. So the solar system, for example, is a nuclear model. It's why the nucleus of a cell was named so. Because it was believed that was where most of the matter, and that's where most of the action is. So we ended up with the classic nucleus with the electrons in orbit around them. He didn't know about he knew about the proton and the electron, but he did not know about the let me get this right. He knew about the proton and the electron. He didn't know about the neutron. That was later discovered, and it was a tricky one to find because while the proton and the electron have charge, and you can create a nice little circuit with some plates and a buzzer that can make some noise when something goes through, or flash a light, a little electron goes in there or a proton goes in there, you can complete a circuit. But neutrons don't do that. So neutrons were actually discovered later on by a secondary reaction that they cause when they hit things. So that's the first bit I really wanted to focus on. The other bit is moving from over to Niels Bohr and the effect that has later on when we learn about waves. So when I look at my cupboards at home and I open the cupboards, I have shelves and my tins and my cups, and they all go on shelf 1, 2 or 3. So I might have bowls here, and on here I have plates, and up on the top I have cups. So I could label them shelf 1, shelf 1 at the bottom, shelf 2 and shelf 3. When this model came out, the first one, there was nothing to say that the electrons weren't all in the same orbit. It was later on that Niels Bohr discovered that actually electrons live in shells. So if I draw them, I like to draw them this way. He came up with the idea of shell models. So we'll go duplicate and make it bigger. And you're expected to know the electron configuration for the first 20 electrons, which are the first 3 shells. So if we now look at our shells, we have 2 electrons. Try that again. We have 2 electrons in the first shell, 8 electrons in the next shell, and 8 electrons in the next shell. Well, the reason I'm making sure we cover this is what happens when they move between shells. In chemistry, we know that all atoms want full shells, but in physics, we can actually manipulate these shells without changing the atom or creating chemistry. So let's take, I'll do it in green. Let's take an atom that's on this shell here. Well, what we've discovered is that we can pump it, we can give it energy by hitting it with an electromagnetic wave. So if we shine a wave in, it can be radio, microwave, we can take this electron and we can, let's put it freely moving. I'm going to do it so I can grab it and move it. So let's draw it here, grab it. There it is. So here we have an electron. We can hit it with that wave and we can pump it up to a higher level. And as we move from one shell to another upwards, so let's put this in red, as we move up, we have more energy. More energy. So while it's in that higher electron shell, it has more energy. Then when it lets go of that energy, it can drop back down to a lower shell. And as it drops back down, its conservation of energy means it has to put that energy somewhere. So it re-emits the energy away. So let me say that again. Energy going in the form of an electromagnetic wave. Energy in moves that up. When it drops back down, it gives the wave back off. Energy out. So, one of my favourite inventors, I can't remember his name, but he famously said this. So any guy who said this is one of mine. The inventor of the laser. And he famously said, here we go. Charles Towns. He famously said, I can't see the point. He'd made a laser. And the reason I'm telling you this is lasers work exactly like this. Quotes, the quote is, he made it and he said, I really can't see any reason for having it. And I don't think there'll be any uses for them. And what he'd actually done is worked out how to take a chamber of gas. So this is how a laser works. Take a chamber of gas particles. So let's go, let's do them red. Like that, and to apply a electromagnetic wave to them, in goes the wave, and this can be powered by a AA battery. It really does not need a lot of energy, plus minus battery, and all of these atoms pump their electrons into a higher energy state. So every one of them gets to a higher energy state. So too big. Let's go smaller. There we go. So there's a nucleus. There's a shell 1, shell 2. All their electrons then pump up to a high state. And the really clever thing is, he figured out how to make them all drop down to the same level below at the same time. Every single one of them gave off an exactly the same wavelength beam of light. So this is why laser light looks so unusual. Every one of those beams coming off every one of those atoms is in unison. And so you get that pure laser light that's created. And in the 60s when he invented it, he couldn't have imagined the uses for it. We use it for data storage, we use it for health treatments, we use it to help us create electronics. It's everywhere, and it also entertains my chihuahua when I shine the light around on the field at night, and the cat. So they're the main two things I wanted to get out of this. The fact that Rutherford's experiment showed us the structure of the atom and what was going on there, and these idea of electron shells and pumping the electron up to a higher energy shell by hitting it with EM waves, and then when they drop back down, they re-emit EM waves. And you can make them emit all sorts of different wavelengths. So you could put in a radio wave and get out a microwave, for example. And this is what we do here. We put in a small amount of radio and we get out light waves. So that is that lesson. Now, I need you to just make sure that you've covered what you did with Mr. Dolan. I'm assuming you've done quite a bit on that. You've done quite a bit on that. The idea of cloud distribution. It's the beginning of quantum mechanics. So I'm not going to go into it too much. And that is it.